Welcome to Math 104, Chapter 1AT, where we talk about functions, graphs, and their models. Now, first up, we are going to be classifying numbers so that when you see it on your homework and they say, hey, put your number into an integer or your answer into an integer or a whole number, we actually understand what that means. So classifying numbers, first up, we have a natural number. Natural is denoted with a double bar and an N. Now, what is the lowest natural number you can possibly think of? Now, most students are between two values. It's either between 1 and 0. So natural numbers are actually going to start at 1 and then tick up from there. So 1, 2, 3, and all the way up. So natural numbers are all positive and start at 1. So all positive and start at 1. Now, whole numbers are probably what you're thinking of before. So whole numbers look like a double bar with a W, and those are the ones that start at 0. 0, 1, 2, 3, and again, tick all the way up. So these are still all positive numbers, and they start at 0. Now you notice down here where you have whole numbers. Now in your whole number, right, we said whole numbers contain 0, 1, 2, and 3. But notice in your whole, it actually has your natural numbers. So sometimes what is missing from some of our charts when we look at it online is actually a little section meant for us, which is a natural number. So if you want, you can add it to this chart. But as you're going to be seeing, we're going to be gradually getting bigger and bigger. So numbers that are rational, which we'll talk about here in a moment, contain still natural whole. And what we're going to be doing next is integers. So now what is missing so far from your whole number or your natural numbers? So we started with 1, then we started with 0, and now we have to keep expanding, which now we're going to be talking about negative numbers. So integers, instead of doing I with 2 bars, that's going to be saved for later, we have an integer. Integer is a Z with 2 bars. Now this is where your negative numbers come in, so we can start with -2, -1, 0, 1, 2, and so forth. So you'll notice that your natural numbers are in here. Your whole numbers are also in here. And now we've then added integers. So integers are both positive and negative numbers. And let's do rational. So now what is missing? So we now have added in the negatives, but now what? So what's missing are any sort of decimals or fractions. So rational is a Q with a bar in it. So this still comprises of negative numbers like -2, -1, ... on either side just means it continues. So this continues down towards negative infinity. We also can include a decimal. So -0.33. It still includes 0. We have fractions like 1/2. We still have natural numbers, and we also have something like that. The square root of 4. Now, what is the square root of 4? Which is 2. Now, rational numbers have a few rules to them. If only it were so nice that we could say, hey, this actually is all square roots and all decimal places. No, that is actually not the case. So if we throw in the mix of decimals, decimals have to have certain conditions. They either have to terminate, so we have things like 1/2, which is 0.5 or 0.50, or your numbers can be repeating, or if they have any sort of pattern. So for example, like 1/3, this is 0.3333 repeating. Repeating is just that bar over it. Or if you have a number, let's just throw it out there, like negative 1.121212, and the 1/2s are repeating, and they can kind of go on. So those are your rules for your decimals. We also have a rule for your roots. It goes for any sort of square root or cubed root that comes out nice and clean, like the square root of 4 or this negative square root of 100, right? Well, this is really 2. This is really negative 10, right? The negative on the outside is okay. The negative on the inside is not okay. So these would be totally fine. You could do it with cubed roots as well. Cubed root of 27 is 3, right? 3 times 3 times 3 is 27. 2 times 2 is 4. It's just kind of going in the opposite. So roots that are clean or decimals that finish or repeat. We can also have irrational numbers. Irrational is another Q with a bar in it, but now it's a star. Now, take a look at the word rational and irrational. The irrational portion of it, right, is the negation of a rational number. So it's the opposite of rational, which means the opposite, we are not allowed to have, well, we can't have negatives. I can't say that. We're not allowed to have any natural whole numbers, anything that comes out nice and clean in a square root, any sort of decimal that has a pattern or a terminate, so it's really the opposite. So can you think of the most famous irrational number? So perhaps you're thinking of pi. Now pi is roughly what? Most of us in class say 3.14. Some of us who have had teachers in the past can repeat the next following, but at some point you're going to have to stop, because this is a continuous number that does not repeat. It does not have any pattern to it. So that goes with your rule. Decimals, they are continuous. They do not repeat. Do not repeat. Or like roots, perhaps we do the square root of 2, which is about 1.41. So any sort of roots that are not clean. So you don't come out very nicely. And you'll notice that irrational numbers are separate from your diagram here. That's because they contain no overlapping. They don't share anything with the others. Now, last we have is all real numbers. All real numbers. Have you heard that before? All real numbers is now with your R and 2 bars in the middle. So this is just saying we have all of the numbers under the sun. So all the numbers that you can think of are going to be considered real numbers. Now I want to take a look and make sure that my mic is actually on. So I'm just going to, okay. I do have a habit at times of not turning on my mic. Okay. So now let's take a look at some number lines. So using the number line below, place the numbers in order from smallest to largest. So I would say pause the video here and see what you can come up with. So if we have -15, that looks like our smallest number. So that's going to go on the end, and let's do the same thing, but for your largest. Largest being 7 over here, so we can X that out. And then let's see, your next smallest number, we're between, let's see, some of your negatives. We got some values over here. So -1 versus -1/3, which is -0.333. So we're going to add that over here, -1 and -1/3. So that takes care of your negatives. Then let's look to some of your other values. Now let's take a look at the square root of 4, which we know now to be 2, or maybe 1/2, which we know to be 0.5. So 2 kind of stands out. We can put that over here somewhere. So we can get rid of that. Directly next to it is pi 3.14 repeating. So let's start to chip away. We also have 0 here, which is a little hard to see. So we can add that here. So now we have 0.44, 0.45. So let's add that, 0.44. And directly next to it, 0.45. Slowly chipping away. Now we also have 0.5, which we'll add right here. And now we are with 3.14 and 3.14 repeating, which that is going to go over here. We got 3.14, and then we have 3.14 repeating, or you can write this as pi. And there you have it. So it seems a little basic, but we definitely want to make sure your foundations are strong, especially because on your homework, it'll say, hey, label or put them in order, or put your coordinates in order from smallest to largest, things like that. Now we have some notations that we have to go through when we take a look at some of our graphs, and this is where it comes in. So if we have a greater than, so if we're looking for something that is larger, so we can have something that looks like this. If it's just greater than, we do not need any sort of bar underneath. That comes into play when it says greater than or equal to. The equal to sign is where the bar underneath comes into play. So if we're trying to write x is greater than 6 in inequality notation, we are looking at the value of x and 6. And x being greater than is going to get the bigger piece of that symbol. Now, if you're someone that has a hard time remembering, well, which symbol is what, think about the word greater. I'll put it up here. Oh, I cannot spell today. So the word greater kind of looks like this sign where the R is right here. So if you're thinking greater, perhaps you think it's the sign that's on the R. So kind of silly, but who knows, it might help. Now, if we're putting it in graph notation, so going from inequality to graph notation, well, we're going to put your 6 somewhere on this line. And if we want values that are greater than 6, we want values that are to the right of the 6. Now, in order to determine right here if we're going to include or exclude this 6 in greater than 6, well, if it's greater than but not equal to, we're going to either use an open circle or we're going to be using a parentheses. Parentheses meaning we are not including. So we are not including the 6. So from graph notation into interval notation, right? How would you read this graph if you were just given the graph? Well, we're starting at 6 and we're going all the way over to a positive infinity. Now, anytime we're talking about interval, we can only use either a parentheses or a bracket. We said parentheses we use when we don't want to include. So as you have written it on your graph, we're going to write it next to your 6. Then it becomes, do we include or exclude your infinity sign? because we are never going to achieve infinity, just like we're not going to include 6, if we cannot achieve or include this number, we have to be another parentheses. Now, this is always parentheses for an infinity. Whether that is a positive or a negative infinity. Now let's try it again with a less than sign. Now, if you're ready for it, you can pause the video, you can try these out on your own, and then you can keep going on the video. So less than is the opposite. So now we are using the backward sign. So something like that. Again, if you are having a hard time remembering which one is which, less than, if we use the word less, it kind of looks like it's that symbol that we have just written that. So again, it being less than and not less than or equal to. The only difference is that less than or equal to, you are now just putting a bar underneath to signify that equal sign. So if we're looking at x is less than 3, we're going from the value of x to 3, and it's x is less than 3, so 3 is more than x, so 3 gets the bigger portion of the symbol, and x gets the smaller portion. Now, if we were to put that on your graph, again, 3 being somewhere here, we are saying, well, 3 is not being included. It's less than 3. So values that are to the left of 3 are smaller. And we are not including 3, so we can have either a parentheses or an open circle or both. And if we're trying to write that into an interval, then we're taking your smallest value. So what is the smaller value, negative infinity or 3? Well, we're going to go from negative infinity all the way to 3. And then are we including these values? No, we are not. So we're going to be using parentheses. Always parentheses if we are working with a less than or a greater than. So let's try it again now with the equal to sign. So x is greater than or equal to negative 15. We are saying this is x. And we have negative 15. X is greater than or equal to 15. So x is more. It gets the bigger portion of your symbol. And if we were putting it on the graph, it is the exact same as the graph, the first one, except with one little difference. This coming from, we are now including the 15. So instead of an open circle, we're going to do a closed circle. And instead of a parentheses, we are going to use a bracket. This just says we're going to start exactly on 15. Or sorry, negative 15. So if we were to put this into your interval notation, we're still going from negative 15 all the way to, what is that? Infinity. Then we are going to bracket the 15, the negative 15, because we are starting on it. And then we need an open parentheses on infinity. We are not including infinity ever. So let's try the last one. If you haven't paused the video at any point, I would definitely pause it now. See if you can give this last one a try. We have x is less than or equal to 1/3. So 1/3 being larger than x is going to get the bigger portion of your symbol. So x is less than or equal to 1/3. Again, putting that onto a graph. Values that are less than 1/3 are to the left. Because we have that equals to sign, we are going to be, we're going to be using your bracket or a closed dot. And I just realized I used the wrong color. And one last one, we are going from your smallest value of negative infinity, going all the way up to 1/3. We have a parentheses always around infinity, and that closed bracket or closed circle around 1/3. So we said, note, we never include infinity. So that will always have a parentheses around that. So now let's talk about set builder. You might see something like this in the future. This is set builder notation. It's basically your inequality notation, just with just an added bit. This says X is a number. So that portion here is very basic. It is just defining what X is, or sorry, that X is a number. And then this part here is the word such that. Such that, or so that. And then the following is what we can put into words. How would you say this next part? X is greater than or equal to. So that's how you can write and read in set builder notation. Really, the big takeaway is that this bar just means such that or so that, and then following it really defines for us what these X values are going to be called. Now, can we take this sentence or even the mathematical sentence, and can you actually put that on a graph? Well, if it says X is greater than or equal to 5, we have 5 here. We said we are going to be greater than, so anything to the right, and we are a greater than symbol. So either a closed dot or a parentheses, or a graph, a bracket. So let's try it again with your next few examples. I would see if you can pause the video, especially if you haven't paused it after the first one. See if you can do it just on your own, like some practice. I'm always going to be here on the video that you can just start and stop as you go. Okay, so how can we read something like this? It says X is less than or equal to -6. So in your set builder, if we're going from inequality into set builder, we're just going to take this and we are going to rewrite it into this space right here. This says X is a number such that X is less than or equal to -6. And if we wanted to write that in interval notation, well, if you wanted to jump to your graph notation, I'm always a huge fan of your graph first. We said -6, and we are less than -6. So values that are less than. We said X is less than or equal to. So we're going to have a closed dot and or a bracket shading to or towards -infinity. So your interval, we're going from -infinity all the way up to 6. We said we do not include -infinity, but we can include your -6. Let's try it again. We are looking at n is greater than 0. So this is just saying n is a number such that, I'm going to drop that down, n is greater than 0. Let's graph it. You have 0. We said n is greater than 0. Oops, greater than 0. So we're open dot or a parentheses, and we're shading all the way towards positive infinity. So your inequality notation is 0. Sorry, parentheses, 0 to infinity, parentheses. One more time. T is greater than or equal to -1. So now we need to say T is a number such that T is greater than or equal to -1. So on your graph, we have -1. We're looking at the values that are greater than -1, and we are greater than or equal to, so we're starting our values at -1. So you have a bracket, -1, and to infinity. And there you go. All right, let's try it again. Now let's go from a graph into interval or inequality notation. So again, if you are already good on this part, feel free to just skip on by. So describe the graph notation. So we are looking at the values that are shaded in the middle. So from 1 to 6, and we have parentheses around them. So in interval notation, we should write parentheses 1, comma 6, parentheses, always smallest to largest, right? So now in inequality notation, we're going to write again your 1 and your 6. We're talking about your x values here. It's always going to be assumed that it's x unless they have told us we're now looking at your range, your y values. And when we go to read this, we're just saying x is greater than or equal to 1, but less than or equal to 6. So we're just going to be using the symbols here. And again, just making sure they match. If you can read it, I think you are able to write it. So one more time here. Now notice that this 5 has a bracket. So we are looking at an interval with now includes -5. We go all the way up to 1, which has a parentheses. So x is greater than or equal to 5, but less than or equal to, less than 1. So we start with your -5, your 1, and we said x goes in the middle. We have a bracket, which means we're going to have an equal sign underneath, and x is less than 1. Okay, we're getting to the end of chapter 1 intro. Now let's look at your algebraic expressions. So we use a combination of real numbers and letters to create algebraic expressions. Which is a set of operations. So just a series of addition, subtraction, multiplication, division, you name it, with one or more variables. That's what it means to be an algebraic expression. So all of these below are different types of expressions. You'll see there's addition, subtraction, multiplication, a few different variables going on. And what we're going to be looking at are how to break these down. So a term, the term of an algebraic expression is the product of one or more variables and a real number. So what that means is that these terms are going to be separated by addition or subtraction. So each term will contain in itself any sort of multiplication or division within it, or a real number. So ours having in this first one, how many terms? Well, a term is separated by addition or subtraction. So here we have 2 terms. So this being one term and another term. Now here, how many terms do you have? Now this one is a little tricky because yes, there is addition and subtraction, but within this whole thing, because it's all being divided by this portion here, this is actually going to be one term. Now, if you do break it up so that this 3x has this one minus this one over this one, then it becomes 2 terms and it becomes split up. This is just one simplified form of it. If you wanted to include plus 5 or plus 5x, whatever it is, because this has a different denominator, this can be considered a second term. And then here, how many terms? Again, 2 terms. 1 term, 2 terms. Now, the real number that we had talked about can be called a coefficient. Now, a coefficient is any sort of multiplication to a variable. So in our case, and I'm going to write that a little bit differently. So if you have a real number attached directly to a variable, that is considered your coefficient. So here we have coefficients. The 5 and the -2 are coefficients of their variables. The 5 is the coefficient to the x, and the -2 is the coefficient to the y. We can also have a real number that's considered a constant. Now this one, if we were defining what your coefficients are, right, they have to be directly attached to your variable. So this 7 is the coefficient of z, but notice that 2 is not attached to a variable. This is the one that is considered your constant. It is a standalone term. It is not attached to a variable. So that being said, if we are looking at the values below, how many terms are there? And can you label either your coefficients and your constants? So let's start with terms. Pause the video if you can. What are your terms? Well, there are 3 terms, 1, 2, and 3. 3 terms for x squared, 3x, and a -7. Now, what are your coefficients? Your coefficients are 4 and 3. So these are your coefficients. And what's your constant? Your constant is your -7. Okay. Now, can we evaluate what your expression is if we were to substitute an x into your value? So when x is equal to 2, we are going to replace the x values that you're seeing and put in a 2. So if we originally had 4x squared plus 3x minus 7, we are going to replace those x values with a 2. In our case, we're just looking at 2. So we're going to substitute it right in. And orders of operation says, please excuse my dear Aunt Sally, right? PEMDAS. It just means that before we multiply the 4 to the 2, we need to multiply or take the square before any sort of multiplication happens. So we have 4 times 2 squared is 4. Then we can go ahead and multiply. We also have access to any sort of calculator. So whether you use Desmos or a graphing calculator of sorts, please feel free. We have 16 minus 1 to give us 15. Okay, that should be it for the following. So hopefully you should feel comfortable figuring out what a coefficient and a constant in terms are and how to substitute values in. Again, big takeaway. PEMDAS, oops, Okay, multiplication and division, it's just based on which one comes first. So if you see a division first, you can do that and then multiply. Same thing with addition and subtraction. So combining like terms. When we combine like terms, we bring together terms that appear the exact same. Now, if we have addition, right? If we have any sort of addition, we can actually go ahead and drop those parentheses that you're seeing and then go ahead and add them together. Now, what I like to do, and I'm sure your teachers have in the past, I like to highlight what looks the exact same. So if we have 5sx, now when I mean the exact same, I'm looking for not so much the coefficient that is the same, I'm looking for the variables that are the same. So the same variable on the other side would be sx. The coefficient just happens to be the same in this case. The other one, we have a negative 2y. So on the other side, I'm looking for a y. Again, this one having a similar coefficient, that is okay. And the remaining, let's see, we're looking for a z cubed, and ours is a z squared, which do those mean the same thing? No, they do not. So this one will just give a different color. So if I were to bring them all together, this isn't necessary, but I like to write out my work one more time. And then anything that I have similar can go underneath. So we had 5sx and it was positive. We have plus a 2y. And we said, well, I can't really add this value to this value. So I'm just going to make a little bit of room and then put my next one. And then from here, all I can do is add and combine my terms. Do you have to do this? Absolutely not. You can just go ahead and add once you're here to your values. Now notice that when we're adding, we're just going to add right down. These two will cancel each other out. Then we have plus 7z cubed minus 4z squared. All right, let's try it again one more time. So something like this, 5sx minus 2y plus 7z cubed minus 2y plus 5sx minus 4z squared. So with this one, because we have a subtraction sign, that does mean that we are not able to drop your parentheses right away. Instead, that just means we have to multiply this whole thing by a -1. How we do that is just by changing all of your signs. So if we have 5sx minus 2y plus 7z squared minus 2y minus 5sx plus 4z squared. A double negative, a negative times a negative will make a positive. Or you can just remember, change your signs. So again, we're going to be adding your values together. I just like showing where these values come from. So for me, I like to stack to show you guys where it comes from. And then from there, you can go ahead and add or subtract. That will cancel. This one will make -4y plus 7s cubed plus 4z squared. Okay. Now, last but not least, we're going to talk about the coordinate plane. So if you can, pause the video and label the following that it's asking for. So let's label your x and y axis. Your x-axis is the one that's down below right here. This is always your x, and this is always your y. So x and y. Then it says label the origin. Your origin being at the very starting point, 0, 0. Now, if we were in person, I would show you the video on how the origin actually came to be. Pretty much some French guy, I cannot think of his name, he got sick and he noticed that there was a fly on his ceiling, and he was able to make a grid on how to map out where this fly was going. And eventually he actually became the founder of geometry, which shame on me for not remembering his name. I really should know it. So your origin here is at 0, 0, your origin. So now can we plot the points? So -3, 1, these are always your x values at the very start. So we have x comma y. So all of the values that you are seeing in front are your x values. And anything following is your y value. So we're going to go ahead and plot those. So we have -3, 1. So -3 over here, and then up 1. And then again, 4, 5. Let's see, 4 over here, going all the way up to 5. We have -2, 2. We have 7, 3. Or sorry, 7, -3. 0, 8. 0, all the way up here at 8. Right, if 0 is your x value, so notice that 0 here on your origin represents where your x is 0. And then if y is a number, we're just going to be traveling up your y scale, your y-axis. And then the opposite is true if we're looking for -1, 0. Well, -1 here is where your x value is negative, like -1. And then your y value here, because we haven't moved up or down, it will remain 0. So that can go right there. Last but not least, let's label your quadrants. So your quadrants are kind of like Foursquare, where you kind of move about. Now this one you might not have seen in quite often. So this is actually quadrant 1. Moving to the left is quadrant 2. Going counterclockwise, 3, and quadrant 4. So these are all of your quadrants defined for you. And I believe that is it as far as your intro goes.